So in this video, I want to finish it off and derive the density of state for one-dimensional and zero-dimensional semiconductor. So shown here is a one-dimensional semiconductor, and what it means is that your electrons are confined in let's say y and z dimension, but they are free to move in x directions. And as a good case of that would be for example a nanowire or a gate all around transistor and so on. And so in this case, if our electrons are free to move in x direction, there they also have k space where they could be represented. All these states could be represented in a one-dimensional k space, and they're separated by again a distance of pi by l. So again, the number of states that I can have is essentially, in a given k space is I have, let's say a length of k in k space. So each of my states occupies this this distance of n over pi, and then I multiply it by 2 to account for the spin up and spin down degeneracy. And it's simple to take a derivative of this, and in this case the derivative of this is essentially just 2 into L over pi. And I know that my density of state, again I'm repeating the same analysis I used for 3D and 2D, that my density of state per unit energy and per unit length in this case is my total number of states per unit energy and divided by the total length. And in this case I have the total length of my nanowire to be L, so I divided by that. And again, I use this chain rule to expand this derivative in terms of k, and then taking this derivative of k with respect to e. And again, I'm repeating the same stuff over again, and I take the ek relationship and use that to substitute into this density of state formula. So I substitute for dE by dk, and I substitute for dN by dk, and finally what I get is, for a one-dimensional semiconductor, my density of state is essentially 1 by L, substituting for dN by dk over here. So I substitute 2L by pi, and then I substitute for dk by dE, so m by h square k, and then instead of k I write it in terms of energy, so I get this relationship, and I already see a lot of cancellation happening. So my L cancels out with this L, and let's see what else is cancelling out. One of these h cancels out with this h, and then I can substitute instead of h bar I can write it as h by 2 pi. So what I get is I get a density of state relationship which is of this form, where it's let me work this out, and so this will come out to be 2 root 2 m to power 1 by 2, and e to power minus 1 by 2. So in this case, it's very interesting. Now my density of state for a one-dimensional semiconductor, it's actually inversely proportional to energy, something I didn't expect intuitively, and it's also proportional to this density of state mass as a power of 1/2. And we'll ponder upon all these together when we compare the energy dependence of 3D versus 2D versus 1D. So to complete my analysis, let me also look at the the zero-dimensional semiconductor. And what, for example, over here you have a quantum dot, and it's really confined in all directions. So it's confined in x, it's confined in y, and it's confined in z. So there's not really a k space or ek relationship for this thing. The closest analogy for this that I can think is it's similar to a single atom, and as we know, in the case of a single atom, what you get is discrete states, and each of these states is occupied by 2 electrons. So the density of states in this case for a zero-dimensional semiconductor, it would be essentially my density of state would be a delta function. So for a zero-dimensional semiconductor, it would be a delta function, and you will have where one of these energy states occur, you will have two of these electrons which can occupy these states. So this would be the case for a zero-dimensional semiconductor. So I finally derived these relationship for 3D, 2D, 1D, and 0D. And if I compare the energy dependence of all these cases, it's pretty interesting. So what I get is typically for a three-dimensional semiconductor, my density of states, it's proportional to e to power of half. And for a two-dimensional semiconductor, for example, you'll have a quantum well or a two-dimensional electron or a whole gas. So in that case, my density of state has no proportionality on my energy, and it's essentially a step function. And 1D, for example, a nanowire, it becomes very interesting, and these things tend to have an inverse relationship with energy, and it's proportional to e to power minus half. And in the case of zero-dimensional, for example, a quantum dot or so, my density of states is essentially a delta function, and whenever there's a state occurs, I can occupy a couple of electrons.